Superposition is the title that we give to the property of waves when we just add them together and we get the effect of the total wave. In particular, we're thinking right now of just adding two waves, but of course you can add more than two waves. And we're going to think about them in particular in two contexts. Interference is generally what happens when you have two waves of the same wavelength, frequency, speed. Of course, these are all related, right? So if you have two of them, then you get the other one. And you're looking at two different points in space. For beats, if you are a musician, then you're probably familiar with this idea. This is the change in volume, pretty fast normally, that you get when you have two sound waves that are almost the same frequency, and they have that warbling sound, that very quick change in volume. And so for these, we're going to think of these being the same x and same speed, but they're going to have a different frequency. And of course, if they have the same speed but a different frequency, they're going to have a different wavelength too. But we're not going to think as much about the wavelength as we are to the frequency. So we're going to go ahead and cover interference in this video, and then we'll do beats in the next video. So we are going to start with a simulation. So here's our simulation. I want you to picture on this left-hand side that we have a speaker. And that speaker is putting out a sound wave, and it's going pretty slowly, so we can actually pay attention to it. And that sound wave is traveling to the right. And we can see it just continuously going here. And so the pressure is getting high and low and high and low as it keeps on going. Okay, now we're going to add another speaker. And the other speaker is going to be on the right-hand side, and it's pointing to the left. And we can see, it's making its high and low, traveling over to the left. While we've got these going, let me just pause it for a second and adjust the time so we can look at a convenient point in time. Oh no, can I undo that? Yes, I can. Let's look at some of the properties of this wave. We can see that the wavelength is 4, and I've put meters as our unit. So the wavelength is 4 meters. And if we were to look at the period of this wave, I've set it to 10. We can confirm that by moving the time, and it took 10 seconds. There's no way to put units on here that I know of. It took 10 seconds for the peak to go down and then back up to here. So we of course could figure out the wave speed from that. But the important thing to note at the moment is that the wave that we have going to the right and the wave that we have going to the left have the same wavelength and the same wave period and therefore frequency. They're just, one is going to the right and one is going to the left. So this is what it looks like if both of the waves are going at the same time. You can see the red one is going to the right, the green one is going to the left. Now, if you stuck your head in between these two speakers, you wouldn't hear the waves individually because they have the same tone, they have the same pitch. What you would hear is the total wave, the superposition of those two waves, and that makes this purple line here. So I'm going to turn off the other two, And this is the result. Right? It basically looks like a standing wave, but this wave is the result of adding our two sound waves together. And there's some important things to notice here. One is that the wavelength is still 4, but in particular, we can see that there are several points that more or less act like nodes and antinodes. That is to say, there are points where the waves add constructively in order to make very large movements. So 2 meters is an example of that. So if you stuck your head right here, this would be a very loud point. And then there are other points, such as 3 meters, where the two waves always add destructively. So if we turned on F1 and F2 for a moment, there's a lot going on. They're always opposites of one another at 3 meters. When one is high, the other one is low. So red is high, green is low. If I move it forward, they're always opposites of one another. So this one is at almost positive, what is that, quarter. This one's at a negative quarter, and so forth. So if you were at 3 meters, that would be a very quiet point. And we could keep on going, right? There are some points that are in between, right? So 3.5 meters. It's neither one, right? It's neither completely destructive nor completely constructive. It's just in between. We are going to focus on how to calculate the destructive and constructive points. And it all has to do with what's called the path length difference. So this is the delta D. To get that, we're going to draw, this was from a demo that we were going to do in class. We don't have that opportunity now, but we are going to basically draw our speakers that we had imagined on there, and then we're going to have our, let's see, so 8, 4, 4, 2, 2, 2, 2, 1, 1, 1. There's a lot of dots. Okay. So that's 8 and 12 and 4. That's good enough. Okay. And the speaker was at 16 and the speaker was at 0. That was the idea. Okay. So what we're going to do for each point, we're going to see how far it is to speaker 1, how far it is to speaker 2, and then we are going to take the absolute value of the difference between those two distances, and that's going to be our path length difference. And then we're going to see how that path length difference compares to the wavelength of the wave. So first of all, remember that we had a wavelength of 4 meters. Okay, so let's pick a point at 4 meters right here. So D1 is the distance from this speaker. So obviously we are 4 meters away in this example. 4 meters. What's the distance between this point and that speaker? It's 16 minus 4, so D2 is 12 meters. What is delta D? Delta D is the absolute value of D1 minus D2. So that's 8 meters between them, and we take the absolute value, so that's the positive 8 meters. Okay, what do we do with that 8 meters? We want to see if there is an integer number of wavelengths that could fit in there. So if you could fit a full number of waves in there, then you're going to have constructive interference. So we're going to take this number and compare it to the number of waves. So obviously, you can fit exactly 2 waves in this 8 meters. And so since you can fit 2, which is an integer number, then this is going to be constructive interference. So if we have an integer number of waves, we have constructive interference. So let's go see if that is confirmed. So we're looking at 4 meters. We can already see that, of course, that was confirmed. If we just play this, then it's already obvious. But there we go. Okay, let's pick a different point. Let's pick 7 meters right here and see how that plays out. So at 7 meters, D1 is obviously 7 meters. D2 is equal to 16 minus 7. It's going to be equal to 9 meters. Delta D is equal to D1 minus D2 absolute value, so that is 2 meters. In order to determine if something is destructively interfering, we want to see if it is a number of half wavelengths. That is to say, not an integer, but there's a half wave left over. So we could write that as n plus 1/2 times the wavelength. So that means 1/2, 3/2, 5/2, and so forth, right? So pretty obviously we have 2 meters is exactly 1/2 the wavelength. So we have destructive interference at this point. If we did 3 meters, we already know that the answer is destructive. If we just come over here, 3 meters is right here. We know it's destructive, but let's just double check. D1 is 3 meters. D2 is 13 meters. Delta D is equal to 10 meters. So the question is that a half integer number of wavelengths? Well, the half integers would be 2 meters, 8 meters. Sorry, I did that wrong. 2, and then 2 is the first half, then add 4 to that to get 6, add 4 to that to get 10 meters, add 4 to that, get 14 meters, add 4 to that, get 18 meters, and so forth. Obviously, 10 meters is on that list, and so this is a half integer. Anything that is not on one of these lists, we might as well do this list too, right? N can be 0 and larger. So this could be 0. It could be 4 meters. It could be 8 meters, 12 meters, and so forth. 16 meters would be the last thing that would fit, right? Because it only goes up to 16. So 18 is not even a choice. So all of these points would be constructive. All of these points would be destructive. Here's an example. It's very much the same thing. I don't think we need to go back over it, but you can do that for practice.